Okay, so yeah, the interactions with the anode come in two flavors. We had interactions with the orbital electrons or interactions with the nucleus. We just said BREMS or X-rays are interactions with the nucleus of an atom. The atom exerts a force, an attractive force. By the way, we call an attractive force in this case centripetal force, okay, which is the opposite of centrifugal force, right? Centrifugal force is like if you take something, on the end of a string, a weight on the end of a string, and spin it around in the air. You'll notice that weight doesn't fall to the ground, right? That weight would rise and would stay level off the ground. You can do that with anything that is heavy and spin it in a circle. If you ever, like with your kids or when you were younger, right, hold somebody by the hands and start to spin around in a circle, right? You notice that their feet pick up off the ground and you can keep their feet off the ground, right? You can sort of counteract the force of gravity with centrifugal force. Okay, good. That's a pull outward, right? Centripetal force is the force that the nucleus acts on the projectile electrons. It pulls in on them, okay? It's an attractive force, said in another way. Okay, so it's called the centripetal force. It's attractive. BREMS X-rays account for the majority of the X-ray beam. The rest of it comes from this type, characteristic radiation, which is an interaction with the orbiting electrons. So there's some things we're going to have to learn. A lot of us have not done physics, and a lot of this comes from the physics section. This book is a cumulative type of book, like most books are. They start at the beginning and end at the end, and this stuff's not at the beginning, right? So we got to learn a few things. So you've learned so far, you know that atoms are what make up matter. You've learned that atoms are made of protons in a dense nucleus. You don't care or need to know right now that the nucleus also has other things called neutrons. Anyways, an atom has a nucleus, a center, very small. Orbiting around the atom are electrons, negatively charged. They have an exact opposite and equal charge to the nucleus. One proton in a nucleus has a charge of +1, +1. An electron has a charge of -1, equal but opposite, okay? A small difference is protons are more massive than electrons. A proton is about 2,000 times heavier than an electron. Not very important for what we're talking about. I also want to give you a sense of scale, okay? Atoms are extremely small, okay? There is something like a billion atoms wide-ish in every millimeter, okay? Something close to that, order of magnitude close to that, right? So take a millimeter of width, about a billion atoms in there. Atoms are, and here's a neat thing, it doesn't matter if it's hydrogen or uranium. Hydrogen the lightest atom, uranium the heaviest naturally occurring atom, they're all the same size, okay? So this is something about chemistry and physics, is that all atoms are the same size. Even though they weigh differently, if I took 100 billion atoms of uranium and 100 billion atoms of hydrogen, they would weigh different amounts, but they would occupy the same amount of space, okay? So here's the deal. The atoms, all atoms, same size, they are all 10 to the negative 10 meters wide, okay? That's 1/10 billionth of a meter, 10 to the negative 10 meters, okay?
Say it again.
All atoms are 10 to the negative 10 meters wide. We measure atoms by the width of their outer shell electrons. Where the outermost shell reaches to, that's how big an atom is, 10 to the negative 10 meters. That unit, 10 to the negative 10 meters, is called an angstrom. To the negative 10 meters. All atoms are that big. Now so that's tiny, right? So let me give you a sense of scale. If the nucleus of an atom were the size of a marble or a pen cap, I have pen caps, not marbles, so let's say the size of a pen cap, the outer shell, the valence shell, is a minimum of a football field away. Okay? So this is the size of a nucleus. The outer shell is a football field away, 100 yards away. Okay, that's the sense of scale for how far away electrons are from the nucleus, how small the nucleus is relative to the size of the atom. Okay, if the nucleus were this big, the orbiting electrons are football field lengths away. Okay, so most of the atom, this is correct at some level of explanation, most of the atom is empty space. Okay, you don't fall through the floor or pass through walls because it's not that you are running into solid, no empty space. It's that there's a repulsive force from the atoms in the wall, the atoms in the floor, and your atoms. So you're not going to fall through the floor, even though atoms are mostly empty space. You've lived your whole lives not knowing that, and you haven't fallen through any floors yet.
And all of the shells are equal distance.
Equal distance from one to the next.
From the next shell.
Mm-hmm. But they're not equal energy differences. They are equal distances, though. Yes.
You are forgiven.
And the reason why all, whether it's like hydrogen or like uranium, that they're all the same size is because of the attraction.
It's the attractive force of the nucleus pulling, and you know, with uranium, with whatever 92 protons it has, right? It has to pull on 92 electrons. It's still only going to be, the outer shell is still going to be the same size as, let's say, hydrogen, right? All those electrons in uranium have to pile into the first shell, then the next shell, the next shell, and the next shell until they get out to the outer shell, right? That's still going to be that outer shell 10 to the negative 10 meters, the same as where hydrogen with only one electron is going to be that same size. Okay, so that's a little bit of intro. Okay, so here's the deal: an atom is happy if it has the same number of positive charges in the nucleus and negative charges orbiting, negative electrons, positive protons. If oxygen has 8 protons in its nucleus, it means it's going to have a neutral oxygen atom has 8 electrons orbiting around it. Okay. And by the way, what are you mostly made of? You're carbon-based, right? But 3/4 of you is water, right? And water is hydrogen and oxygen, okay? H2O1, right? So you have more hydrogen atoms than you have oxygen atoms in your body. You're mostly hydrogen, okay? With some oxygen. You're about mostly hydrogen, other parts oxygen. That 75% of you, hydrogen and oxygen, right? Most of it's hydrogen, okay? Anyways, an atom is happy when it has an equal number of positive and negative charges, okay? The electrons around the atoms will arrange themselves into shells. Now, there are rules for how many electrons can fit into any shell, okay? I'm not going to go over the rule right now, but there's a maximum number that can fit into any shell, okay? If an atom, like, let's count real quick because I didn't bother. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is atomic number 10. Can we tell me what atomic number 10 is? Can I bother remembering it? Nitrogen? No.
I need my glasses.
I'm going to go over there. I'm going to go over there because I want to know. I can't remember. I'm not doing physics right now and I don't bother remembering if I don't know.
Nickel?
Nickel, neon. I should have known that because its outer shell is full. Okay. Okay, so you are looking at an atom of neon right now, okay? Why neon? Nothing special, okay? Neon, by the way, is what's called a noble gas. That's why it's on the far right of the periodic table. Those light blue shades are noble gases. They're a little special, not for our purposes though. Anyways, you have an atom of neon, okay? 10 protons in the nucleus, 10 electrons orbiting in total. 2 in the inner shell, 8 in the outer shell. Neon's happy, okay? In comes an electron, okay? Remember, our anode's made of what? What material? Tungsten. So substitute tungsten in here eventually, but right now we're using a small atom to make it simple, okay? Tungsten has a lot of electrons, and when you show all of them, it gets a little confusing. We're going to start with something simple. So take an atom of neon in this case, bombard it with an electron, okay? If the electron happens to pass into the atom on a trajectory that puts it interacting with one of the atom's electrons, what's the force between 2 negatively charged particles? Say it louder.
Repel.
They repel. It's a repulsive force, right? So this projectile electron comes in, happens to be in a position to run into the orbiting electron that was happy inside that atom, okay? Both the incoming electron would be deflected, and the orbiting electron can be deflected, okay? Now there's a trick here that we're going to have to learn. This orbiting electron that's sitting happily in its spot, in its shell level in an atom, it's held onto the nucleus. Remember, the nucleus pulls on electrons, right? You learned that from Brem's radiation, okay? The nucleus pulls on electrons. These electrons are all being held into that atom because the nucleus is pulling on them. There's a certain amount of force binding the electron to the nucleus, okay? We call it binding energy. There's an amount of energy that is holding that electron in place. You have to use that much energy or more to remove that electron, okay? Each shell has binding energy. There is less and less binding energy the further you get from the inner shell. The outer shells are held in with less energy than the inner shell, okay? Kind of like you're standing here on Earth, right? Held down to Earth, but if you put me, a couple hundred kilometers up, I'm not held as tightly to Earth anymore, and then I can just kind of orbit around Earth floating around, right? I'm not held as tightly. There's less energy holding me down. It's similar in a way. Okay, so if the incoming electron is in the right spot and has enough energy, it can eject one of the electrons in one of the shells. When that happens, both electrons leave the atom. This is the incoming electron, it's deflected, we don't care about it anymore. This is the orbiting electron that was here, it's deflected and we don't care about it anymore, okay? What's important now is that we've left an opening here, okay? And next rule to learn is, all atoms try to seek out their ground state, the state at which all of the particles are at the lowest energies possible, okay? I'm in a position of the lowest energy that I could probably get to a little position of lower energy if I laid on the floor, but assuming I want to stay standing, I'm at my lowest energy position, okay? However, if I stand up on this chair, I'm higher off the floor, right? What would happen if I fell? I go boom, right? I fall and go boom, okay? I have less potential to injure myself if I'm standing on the ground versus standing on the chair. That's why it's more dangerous to get up on chairs and do things than it is to do things from the ground and like reach with like a long pole and grab stuff, right? That's why OSHA doesn't want you climbing up on chairs because you're in a position to fall when you're on a chair, okay? I climb a ladder, the higher I go on the ladder, the higher I am in potential space, okay? I'm in a higher position of potential energy, okay? It took work to put me up onto the chair. What did I have to do to get up onto the chair? Use my energy, right? Where did I get that from? I didn't get it for free. I had to eat a hamburger or something, right? Okay. Drink my coffee this morning, right? Coffee's a little bit fake because there's no real energy in coffee. It just blocks the adenosine. But importantly, I had to eat some, eat my breakfast, right? Eggs and bacon or whatever, right? Have my breakfast, come in. I took that free energy from the eggs that I was eating and the pig that we took its bacon from, right? Took that free energy from that animal protein and sugar, and I'm using that now, right? Part of that energy was used to pick me up off the ground, okay? So now I put energy into me being in this position, right? And if I fall, I can now put more energy into me hitting the ground than if I were on the ground and fell, right? That's why falling off a building is worse than, falling down when you're walking down the street, right? Falling off a 10-story building is probably fatal, where falling while walking down the street is usually not fatal, right? You're in a high potential position, okay? The same thing is true in atoms, okay? When you are in a position here, and there is now a space underneath you, okay, you can fall into that space. Being further away from this nucleus of the atom is like standing on that chair, okay? It's a high potential energy position. It takes more energy to put me up here than it did to have me down here, okay? I'm at my lowest energy position when I'm standing on the ground, and I'm at a higher energy position when I get on the chair. This electron is in a high energy position because it's not as low as it can be, okay? When this atom was happy and neutral and all these shells were full, this electron could not get to here. It was in its lowest energy state. It's like being on the ground, okay? But now, this electron is gone. It's as if somebody took the floor away from me, okay? And I fall, right? So if he moves the floor down 10 feet, well, I'm going to fall 10 feet till I hit the floor now, right? So that's the same thing is true. all atoms want to be in their ground state, the position in which all electrons are in the lowest possible shell positions, okay? You move down a shell, you are in a position of less energy than when you were a shell level higher, okay? Yeah.
So, when you have a current, and the current is moving, the electrons move from, they're moving, they're being pushed from the source, but they're also being pulled by the atoms needing to be filled.
Yes.
Okay.
Yes, the charge. The atoms needing to be filled is another way to say the charge. Yeah,
Okay.
absolutely.
Okay.
Yep. That's why we call voltage the potential difference, right? It's an energy pulling you this way, right? In this case, a neutral atom loses an inner shell electron. Now that electron is in a high potential energy position, right? And it can fall to a position of low energy. It's kind of like us accelerating current through a circuit.
I.e., if you stick your finger in the socket, you'll get shocked.
Yeah, it's going to conduct right through you. Exactly.
But because your body is lower potential
Yes.
than the outlet.
That's the idea, yeah.
Okay.
You got it. Okay, so here's the picture. We have to name the shell levels, and for no good reason, the shell levels start with K at the inner shell, and we count down the alphabet from there, or up the alphabet, however you want to say it. So we go K shell, L shell, if there was another shell, it'd be the M shell, and then N and O and P, okay? Also remember, some of you who've been with me for long enough know, there's a rule for how many electrons fit in each shell. Not important right now. K and L are the only shells shown here. The inner shell is called the K shell. Again, K doesn't mean anything. It's kind of like on an EKG where we say, here's the P, Q, R, S, and T wave. They don't mean anything, right? P means that's the P wave, right? But P doesn't stand for anything. K does not stand for anything here. It's just that the beginning of the alphabet got used by other things, okay? So we don't say A, B, C, D. We can instead say shell 1 and shell 2. That's okay too, okay? But we like to say K shell. Anyways, so what we'll say is you have a K shell vacancy. Why do you have a K shell vacancy? Because one of those projectile electrons ran into the anode face and has popped out one of the K shell electrons from that anode's face's atoms. You have a vacancy here. It's, again, like the floor dropping out from underneath me. Here I am. The floor has now dropped out from underneath me. Now I'm going to fall as far as I can. I'm going to fall to, to the next floor down, let's say, okay? When this electron falls to this position, this is a position of high energy. This is a lower energy position, okay? You have to account for the difference in energy from here to here. The electron will have lost energy when it's sitting in here. We know energy is not lost, energy is converted, okay? The amount of energy lost from moving from here to here is emitted as an X-ray photon. So then the next thing we need to know is how much energy does an electron have when it's sitting here, and how much energy does an electron have when it's sitting here? And it's different for every atom, okay? There's how many atoms on the periodic table, and every one of them is different, okay? So you're not going to learn all of them. You're going to learn one of them, because it's easy to learn one thing. So here's tungsten. So it gets a little more complicated when you show a bigger atom, right? We were looking at neon, now we're looking at tungsten. Tungsten's much larger. Sorry, I have to double check something. Okay. Okay, so here we have our tungsten atom. We have our K shell here, our L shell here, M, N, O, and P, okay? Notice each shell has a number of electrons in it. The number changes with each shell. Roughly speaking, the number of electrons in each shell goes up as we move out. More electrons can fit into the outer shells than can fit into the inner shells, with a small caveat that you'll notice the outermost shell only has one electron in it in this case, okay? Would also mean you would find tungsten on the periodic table towards the left side. Won't go into that right now. Tungsten has all the way up to a P shell. So here's the deal. The K shell, remember electrons have negative energy, right? I said don't worry what negative means, don't worry what positive means. I want you to continue to not worry what they mean, okay? Negative, it's not like if I say negative 69, it's not like as if that electron owes me 69 kV worth of energy, okay? Normally in everyday talk, if I say I have negative $69, that means I owe somebody $69, right? That's not the case here. Negative is just an opposite kind of energy to positive, okay? Doesn't mean we're lacking energy, it's just a different kind. So you have to get rid of that if that's bothering you at all, okay? The negatives, don't worry about them. Anyways, this has an energy of negative 69, and the unit we use is kilovolt or kilo electron volt. So you'll see kV or keV as the unit of energy. It's 69 kilo electron volts. The next shell up is bound with negative 12 kilo electron volts, okay? Which shell is held in tighter, negative 69K shell or the L shell at negative 12? Which shell is bound with more energy?
The negative K.
Yeah, the
Because
K
it
shell.
has more,
Again,
there's more electrons pulled towards it.
this number is bigger, right? Remember, don't worry about what the negatives are, right? This number is a bigger number, okay? There is more energy holding the electron in place. It takes more energy to pull out one of these electrons than it does to pull out one of these, okay? Good. So, if you take one of these electrons and remove it, one of the L shell electrons needs to fall into that space. Okay, let's show that.
Think about the line at the snack bar. Everybody's all slumped up at the counter, right? But surely where you get.
So let's say this electron is removed because some projectile electron coming from cathode to anode runs into this electron here, okay? You remove this electron. By the way, how much energy does it take to remove that electron?
69.
Yeah, kV worth of energy, right? Good, okay. Or more, right? So let's say it like this. In order to make K shell characteristic radiation, if I make a setting on my machine below 69 kV, then I cannot make any characteristic K shell X-rays, okay? Because below 69 kV, remember kV is your maximum energy for your projectile electrons, right? And below below 69 kV, none of the electrons you're sending across that gap will have higher than whatever you set, right? So you set 65, all of your electrons, projectile electrons, are 65 kV or less, okay? So if you set 69.5 or 70 kV, then you have some of your electrons are moving that fast, okay? And they can eject this guy. So here's the deal. You eject this guy, okay? One of these falls into this position, okay? So what you'll do is you'll subtract the negative 12 from the negative 69, okay? Negative 69 minus negative 12. Double negatives turn into a positive. Negative 69 plus 12 is negative 57, okay? So the difference in energy from K shell to L shell is 57 kV. An electron falling from L shell to K shell, in order to fall into here, this one had to be gone, okay? This one is gone now. In order for this one to fall to here, it's going to lose 57 kV worth of energy. Again, don't worry about the negative, okay? The X-ray photons that we produce have no electric charge, so negatives don't matter, okay? It's just 57 kV worth of energy. Electron falls to here. It has more energy here. This number is closer to 0 than this number is. This falls to here. The difference is 57 kV. The X-ray photon produced will have exactly 57 kV worth of energy. Every time. Every time a K shell electron in tungsten is ejected, then the L shell falls into place. The X-ray photon emitted will have 57 kV worth of energy. No more, no less. Okay? Every time. No matter how much energy the incoming projectile electron used to get rid of this. Okay? If it got rid of this K shell electron, the characteristic X-ray produced will always have 57 kV worth of energy. This is why we call it characteristic radiation. Because if this were not tungsten, if it were a different material, the different materials have different binding energies for their electron shell levels. So a different material produces different characteristic X-rays. If we used, instead of tungsten, let's say it's a mammographic X-ray machine, an X-ray machine used for mammography, breast imaging. It's made of molybdenum, the anode disk. It's going to produce different characteristic X-rays than our tungsten anode will produce. This is why we call it characteristic. So what you get you get spikes. Instead of a big curve like we get with Brem's rays, you only produce specific discrete energies, okay? K-shell X-rays are coming from up here. So this one here at 57 would be if an L-shell electron falls into the K-shell position. These other ones would be other shells falling into the K-shell. Okay, higher shells falling into the K-shell, which can happen. Okay, I only showed you L falling to K right now, but M could go to K, N and O and P could also go to K, and they produce different characteristic X-rays. Okay, let's do one for example here. Let's say, just for toy model, this one's easy. What shell is this? The N shell. Let's say one N shell electron falls to the K shell position. What would be the characteristic X-ray produced? What energy would it have? How much? 68. How do you know that? You're right, but
because the difference between the two.
how much binding energy was the N shell? What was the binding energy for the N shell?
69.
The N.
And
1, negative 1 or 1, right? And the K shell is negative 69, right? Negative 69 minus negative 1 is negative 69 plus 1, so 68, negative 68. You learn that the negative doesn't matter, so the X-ray produced is 68 kV. Let's go back to this. One of these, probably the one there, is our 68 kV spike, okay? We only produce discrete energy levels. Down here would be X-rays coming out of an opening in the L shell. So M falls, M falls to L, N falls to L, or O falls to L, right? Those are your three characteristic spikes here at these, a little bit below 10, a little bit more than 10, a little bit more than that energies, okay? So K shell produces things like 57 kV, 66 kV, 68 kV, and 69 kV. 69 kV would be if the P shell, or like the O shell, fell to the K shell position, okay? Notice the binding energy for the O shell is teeny tiny, negative 0.01. This one's not even listed because it's so small. Basically, it's 0, right? This one can be ejected real easily from the atom. It's held in so loosely it could fall out pretty easily, okay? Which is why tungsten's a good metal. Remember, metals have loosely bound orbiting electrons. There's your loosely bound orbiting electron. Now you know why it's loosely bound. Because it's held with less binding energy, so we can hop around more, okay? It doesn't take much to remove this, so if this happens to fall to here, you get a very energetic X-ray. This is like me climbing to the top of the building, right? I've got a lot of energy when I'm at the top of the building to lose, right? Okay, that's our characteristic, this is our characteristic graph, number of photons produced, and you only see characteristic spikes when an electron within the atom falls to an open position, okay? This creates what we call a characteristic cascade. So think about it like this, right? If the K shell is open, this is kind of confusing. Let me go back to this picture real quick. I'll go back. If the K shell gets opened, right, then let's say the L shell falls to the K shell. We know what energy the X-ray photon will be. It's 57 kV, right? But remember, the L shell fell to the K shell. So now there's an opening in the L shell. So the M shell will fall into the L shell position. Some characteristic photon gets produced. What's the difference between 3 and 12? Well, it's 9, right? The X-ray produced when M falls to L will be 9 kV. Okay. Then we have now an opening in the M shell. Okay. The N falls to M, right? whatever the difference between 1 and 3 is, so 2 kV worth of energy is produced. And now you've got an opening here. So O shell falls to N. You get this characteristic cascade, right? You make one opening here, L to M, or L to K, M to L, N to M, and so on, okay? Cascading like that, with the added caveat that the extremely low energy ones that we're producing from these outer shells falling in just a little bit are making very low energy photons. Most of those get filtered out from our aluminum, okay? So they still exist, we're still making them. And again, the point about characteristic radiation is if this were something different, if this were not tungsten, we would have different characteristic X-rays produced. We don't do different ones because it's hard enough to show you one, right, until you remember that one. But so you have to remember what the characteristic X-ray is that's produced with tungsten, which means you need to remember tungsten's binding energies. Okay, at least the innermost shells, K, L, M, those are the ones that matter. Okay, you got to remember those binding energies so that you can figure out what the characteristic X-ray that they produce is.
So we build X-ray units basically using the same type of material because it produces a consistent.
Yeah. Your X-ray machine and my X-ray machine both use tungsten anode faces because we know the type of radiation that's produced with tungsten. We know what its characteristics are. We know the characteristic X-rays it produces. Yeah. We have consistency between yours and mine, right? So this is a graph just showing you number of photons produced at increasing or decreasing energy levels, right? This bell curve is your Brem's X-rays. Notice most of your Brems are happening right in the middle, okay? More at lower, but remember we filtered those out. A lot of Brems happening here, less Brem's radiation happening at high voltages. Okay, so the higher your kVp setting, the less Brem's X-rays you have. These are your characteristic spikes. The spikes that are too low got filtered out. Okay, so now we have spikes down at the low end. Most of our characteristic rays are at the high end. What do you notice here about when characteristic rays happen versus when the Brem's rays are going away? Is there a relationship? Where do you get most of your characteristic X-rays? At what energies, high or low? Yeah, we're on this graph, where are there more characteristic spikes at? High, right? Where do you get the least Brem's X-rays? Remember, this graph is a little bit of a cheat because the Brem's actually goes like that. In really, but we filtered out the low energy ones. So this bell curve is not actually a bell curve. So here's the thing. At high energies, we make characteristic X-rays where our Brem's rays were decreasing. Okay? So the Brem's X-rays decrease at high energies, but now we start to make characteristic X-rays. So our beam stays strong at the high energies because of characteristic X-rays. As kV increases, you make less Brem's radiation, and you start making characteristic radiation to counter for it. Okay? More characteristic at higher levels, less at lower levels. More Brem's X-rays at lower levels and less at higher levels. They sort of pick up where the other falls short. Okay? Which is really nice. It's really nice that this happens to happen. Okay. We're almost there. So here are things that can affect how the X-ray beam is produced. The X-ray beam spectrum. Now the X-ray beam spectrum is the range of energies that will be in the X-ray beam. The target material will change the X-ray beam. We just said if you use molybdenum versus tungsten, you're going to produce different characteristic radiation. Your Brem's bell curve will be shifted to lower energies, okay? So target material matters. Mass matters. Mass affects the energy spectrum. Not as much as everything else, but mass changes how many X-rays you'll make. With more X-rays produced, you have more chance to have a wider range of energies. Filtration, those aluminum discs, The built-in filtration as well as this added filtration change the energy spectrum. Filtration takes away low energy X-rays, so you're changing the spectrum. Again, the analogy for that, the best analogy that I like for that is cloudy day, overcast day versus sunny day, right? Understanding that the light you receive changes. KVP. KVP literally just is the controlling the energy of the X-ray beam. It's your, assuming everything else stays the same, right? You don't change your X-ray tube's filtration. You saw where that fits in the X-ray tube, right? That's like inside the thing, and you got to take the thing apart to get to that. So you don't mess with that, right? You're not taking X-ray tubes apart. You don't mess with filtration. The target material is fixed, right? They're only saying in principle, right? No one's going into your room and changing out your anode's target, because you learn the anode is inside of the sealed X-ray tube, non-serviceable, so that doesn't actually change in the real world. Target material doesn't change, filtration doesn't change, generator type doesn't change. Unless you get a new machine, your generator stays the same. The actual variables that you do change are kilovoltage and mass. Kilovoltage does not change the X-ray beam's energy. KVP does. So the only actual one of these that does anything real in the real world is KVP. Okay? But in principle, all of these can have an effect. Again, in practice, they're not being changed. Okay, good. Let's finish this up. A couple more things here, then I'll give you guys some time to get ready for the final, and we'll get this done for the day. A little bit about KVP and mass, okay? This is a rule, and we're going to reinforce this rule later down the road, but let's real quick before we go into this, remind ourselves what KVP does. So let's talk about in the X-ray beam, what is KVP controlling? It's voltage. But that, yeah, we will go to that, but I want to talk about like in the X-ray beam. So you make a setting on the computer, but your X-ray beam, how does your X-ray beam change with increasing or decreasing voltage? Let me rephrase this. Did you make characteristic radiation at low kV settings? Like what was the minimum setting needed to make characteristic radiation? That's the characteristic X-ray that was produced, but the minimum is 70 kVp, 69 or 70, right? The kVp setting changes the energy spectrum. That's the whole point of hang on. That was the whole point of this, what I just did. This right here. Talking about this. The whole point was that kVp is the main thing that changes the X-ray beam's energy spectrum. Okay? So kVp changes the X-ray beam's energy spectrum. How is it doing that? What is KVP doing inside of the X-ray tube during the exposure? What's its role? It's the push for the electrons, right? It's the voltage is the push, right? And with more push, the electrons can travel faster, right? Giving them more kinetic energy to give up. Okay? More kinetic energy for the electrons to give up means more energetic X-ray beam. So there's a relationship between KVP and the energy of the X-ray beam. What does mass, MAS, control in the X-ray beam?
Speed.
Not the speed. Remember, voltage controls the speed of the electrons. How many X-rays you make, right? KVP's factor is to control the energy of the X-ray beam. That's voltage, energy. We're going to really drive this home in the next module. KVP's job is energy, okay? MAS, mass, its job is quantity. How many X-rays you produce and how energetic are they, okay? You need a certain amount of X-rays and they need to have a certain energy to pass through the body, okay? There's a minimum energy necessary for every body part, and there's a minimum quantity of X-rays necessary for every body part. I can have all the X-rays in the world, but if they don't have enough energy, they're not going to get through the body, okay? And I can have enough energy, but if I don't have enough X-rays with that energy, then they're not going to get to the body. They're not there to begin with, right? So you need both energy and quantity, KVP and mass, okay? So let's talk about how these two play with each other, or play together, okay? So radiographically, a 15% increase in kilovoltage is equivalent to if you doubled the MAS. So take a mass number. Let's play with this for just a second here.